Cool. So then the next topic we're going to talk about is substitution reactions involving halogenoalkanes. So you'll see in these examples here, we're always going to start with a halogenoalkane. So our starting molecule will contain a halogen, and we're going to substitute it with something. And in this case, we're going to form alcohols, nitriles, and amines. So these are the three main substitutions that we're going to talk about. And they're all exactly the same. The only difference is the product that you're going to form at the end, which is different. So I'm not going to go into great detail about it. I won't spend like 10 minutes on each topic. What I'll do is I'll run through it quickly, and then we'll just look at a couple of examples of where this could be useful. Cool. So if you do substitution with water, so you need specific conditions, heat and reflux. If you look in the textbook on page 219, they'll explain to you what reflux is. There's a very nice picture in the textbook on page 219. It's an apparatus that we have in classroom. You've seen it before. It looks like the distillation apparatus. The only difference is you turn it upright instead of sideways. So usually when we do a distillation, you see the machine that looks like this. And then the water comes out here. In this case, we do the same thing. We just use that little tube, but we sit it upright. But just go to page 219. You'll see what I'm talking about. Also, that's under reflux. And these specific conditions are very important because they like to ask these in questions. So in a structured paper, they might ask, for example, I want to do a hydrolysis of a halogenoalkane. What are the specific conditions that need to take place? And you need to say things like heat under reflux. Also, the special conditions are very important. Also, just as a very simple example, you'll see here that we start with a bromine atom connected to the carbon. Don't worry about this in the middle here. That's not important for now. But what you'll see at the end is all we've done is substituted the bromine on the left for the OH on the right. So I started with bromoethane and I ended up with ethanol. And it's called a substitution because you can literally think of it like a soccer match. One player goes off and another player goes on. It's not an addition reaction because we're not adding the OH group. We're substituting it for the bromine group. So not like addition when we did addition to alkenes. Addition to alkenes, we literally took one molecule and we added other things to that molecule. So these are all substitution reactions. And again,
so sir,
yeah, talk to me.
I have a question. Yes,
of course.
So this is a substitution because it can't be addition because it's too saturated. That's why we run. 100%. That's why they kick each other out.
Correct. We kick each other off. So it has to be one on, one off. So if you have 11 players on the soccer field, you can't have more than 11. So in order to put a new player on, you have to take another player off. So it's a substitution reaction. One guy comes off and the other one comes in. And you'll see later when we talk about the terminology in a bit more detail, we'll talk about this word nucleophile. So in actual fact, everything here so far that we're talking about, as far as the substitute goes, the substitute in every case is going to be what we call a nucleophile. So we'll talk about what that means. So again, don't worry about how unfamiliar the molecule looks. You identify the functional group and you identify the specific conditions. So here you identify the bromine, you identify under reflux with water, and you identify the product as the OH group. And again, you would not be expected to name complicated molecules like this, but you would be expected to know that under these conditions, I'm going to get that substitution taking place. Cool. So if you see a bromine, if you put it under H2O and reflux, we're going to swap the bromine for an OH group. Also, we can just do a couple of more examples while we're doing this. Somebody just give me a number of carbons.
5.
5. So we're going to draw 1, 2, 3, and I'm going to draw that like that just to make it a little bit ugly. Can we put a double bond in there somewhere?
Yes,
the first one.
There. Okay, so you want a double bond there. And then we need obviously a bromine atom somewhere. So let's put a bromine atom here at the back and here. Cool. And then they're going to be very specific with the conditions. It's not going to be H2O steam or H2O gas like it was with the addition. It's going to be H2O reflux. Cool. So very important, it's H2O reflux. If we did H2O gas, in other words, steam, we would get the addition reaction. So we don't want the addition reaction, we want the substitution reaction. So I'll leave that there, but I'll just remind you that we don't want that. So we want H2O reflux. And then it's quite straightforward. You can draw the product. The double bond stays the same because we're not changing that. That's all the same. And the only thing is we change the OH on that side. Cool, but the rest of the molecule stays exactly the same. We don't alter that. Cool, everyone happy with that? Any questions?
No.
You're good, good. But can you see how important the specific conditions are? This is H2O reflux. It's not H2O gas as steam. H2O gas as steam would have given us the addition. So if we look at that as an example, if we do exactly the same molecule there with bromine and that over there, and we did H2O gas, we're going to get the addition product. So in this case here, we'll get, I'll scroll down a bit, we'll get the, put the bromine back where it is, keep the double bond there, and then we can get the OH added on that side. And in that case, this would be addition. So this is addition. Cool, so very specific. Keep an eye out on the conditions. H2O gas leads to addition. H2O reflux leads to substitution.
Sir, why is the bromine still there? Doesn't it become HBr?
In this case over here, where the screen is?
Yeah.
Very good question. And the answer is because it's an addition reaction, it's not a substitution reaction. So in this case, I'm focusing on the double bond. So my focus here is on the double bond and adding to the double bond. So can you see how confusing it? Yeah. Can you see where we're going with this? The important part is to identify the functional group, identify the specific conditions, and then ask yourself what's going to happen to the molecule under the specific conditions. So you have to learn to ignore the rest of the molecule and focus on the specific conditions of the reaction. Cool. So in this case over here, we ignored the double bond. So I'll do that in red like I did over here. We ignored the double bond and we focused on the bromine. We focused on the substitution of the bromine. So we focused on that. Yeah. And we focused on that over there. Good. So very good question. Thank you for that. That's an excellent question. Okay, then you can go back and then we can carry on looking. So that would be substitution where you get an OH group. Then you can also do substitution to get what's called the nitrile group. It's part of your functional groups. You just need to learn it. It's the C triple bond N. Also, it's the C triple bond N, and it's called a nitrile. And this carbon here can't have any hydrogens on it because it has to be connected to something on that side of the molecule. So there's no hydrogens on that carbon over there. And exactly the same thing, you just need to learn the specific conditions. And in this case, you have to have KCN in ethanol. And then what you'll see is we take off the bromine and we add the C triple bond end on that side. Ooh, and then don't worry about the way that it's drawn. They've just rotated that bond. So all they've done from there to, oopsie, let's do that. All they've done from there to there is they've rotated that carbon. So they've rotated it. Instead of putting the CN at the top, they put the CN on the right-hand side. So I could have easily just have drawn this as CC, and I could have put the C triple bond N over there. Ooh, but that's exactly the same molecule. So that would have been exactly the same. Exactly. I'm not saying it's a different product. I'm saying that's the identical product. We've just rotated about that bond. So the CN is still over there. And this is quite useful because you'll see that we've added one more carbon atom. You'll see later, we can actually do something more with this. We can take short chain alkanes and we can lengthen them. So we can turn like a 6-carbon molecule into a 7-carbon molecule, for example, which could be useful for some kind of reaction. We don't know what, but it could be useful for something. Also, we can increase the number of carbons in a molecule by doing this kind of reaction. So here's a good example. Ignore that. Focus on the bromine, focus on the chemical, and realize that it's just a substitution reaction that looks like that. They used NaCN, but it's exactly the same as KCN. It's just a different group 1 metal. So the important part is that you have the CN inside whatever you're adding, or the substitution thing.
So it doesn't have a triple bond there.
It does, you just don't see it. So they've drawn it as a kind of skeletal formula, and you have to remember that if C has a bond on that side, that's 1 bond, and if it's bonded to an N, it implies that it has to be 3 bonds in the middle. So it's implied that it's
it's implied.
Correct, correct. So whenever you see CN, it's implied that it's C triple bond N, because carbon has to have 4 bonds. So there's the second bond, the third bond, and the fourth bond. So if you look at it over here, that bond is this bond, and there's 3 bonds between the carbon and the nitrogen. It's exactly the same as if we were going to draw an OH, if you know what I mean. So if we were going to draw an OH, we often we leave out the H, the bond in the middle. So the bond in the middle is not important. But good question. Thank you for asking. That's very important. You're basically recognizing it as a functional group. When you see CN, you think of nitrile, and when you think of nitrile, you think C triple bond N. So it's a functional group. And then the last thing that you can do is you can substitute, you can use ammonia, and you can get the amine. So if you look at this one over here, don't worry about all the delta positive, delta negative stuff. Just focus, there's the bromine, and it ends up as an NH2 over there. So all we've done is we've converted bromine into NH2. And you'll notice that NH3 loses a hydrogen. So that was 3, and that is 2. And the reason is quite simple. Nitrogen can only have 3 bonds, so it has to lose a hydrogen. So one of those hydrogens is what comes off and forms the HBr at the end. Cool. Because nitrogen can only have 3 bonds. Cool. So unfamiliar molecule. You can identify the carboxylic acid. So you can say, okay, there's a carboxylic acid, there's a carboxylic acid. But what we're mainly interested in here is the chlorine, because I'm heating it with ammonia, heat and pressure with ethanol. And that's going to do nothing to the carboxylic acid. It's only going to do the substitution to give me that. So I can ignore the carboxylic acid groups completely. So notice that we can completely ignore the carboxylic acid groups. And then here's where I said it. Recall that nitrogen can only have 3 bonds, and therefore ammonia becomes an amine and it loses a hydrogen. So that's just a simple substitution where we took off the chlorine and we turned it into an amine. Halogenoalkane, general conversion. Oh, and then you can also do the elimination. I'll let you go home and read this. This literally just means we take off the halogen, you remove it, and you remove another hydrogen, and you end up forming the double bond. And the specific condition here is sodium hydroxide in ethanol. Cool. And then although all the products are written in the equation above, remember that we're only interested in the functional group conversion. We actually don't really care about all this nonsense on the left-hand side here. That's not important. The most important thing is that we have this molecule on the left. Let's highlight this molecule. No, don't do that. Let's highlight the molecule. We have this molecule here, and we just want to turn it into that molecule there. All of this is just waste. So that's just waste. When I say waste, we're not interested in those products. We filter them off and we throw them away. If we can recycle them, great. If we can't, too bad. So what I want you to quickly see is if we look at if we go back to our functional group conversions, you can now start filling in the gaps. You'll see we've actually covered quite a bit. You should see which one this is. This one here. There we go. So can you see halogenoalkanes are quite central over here? If you look where they are, they sit over there. And can you see that they go off in all directions? They're kind of like in the middle of everything. So if you clear this diagram quickly, if you take away all of that, get rid of the nonsense in the background.
Alcohols.
And alcohols, correct. They're very central. Alcohols, absolutely. Thank you for saying that. We'll get back to that later, but alcohols are definitely very important. But if you start with your halogenoalkanes, you'll see we can form the alcohol, which is heat with dilute alkali, or in the case that we saw, heated under reflux with water. Ooh, we can form the amines under pressure with ammonia and alcohol, and we can also form the nitrile. You see the nitrile is not on here. Ooh, so you would have to add an extra box somewhere, and you would have to say, okay, here's an, hang on. You would have to add another box, and you'd have to say nitriles. Ooh, and then you could have an arrow going towards the nitriles over there. Ooh, and then we did that as well. And then you can also see that if you think about it, we can go backwards. We can take the halogenoalkane, and we can go backwards then to go from the halogenoalkane to the alkene, because we can do the elimination. That's the last thing you can go back and read. But can you see that that arrow is not on the picture? That arrow is a backwards arrow in the opposite direction, like that. So we can also take the halogenoalkane and turn it into back into an alkene through the elimination. Sorry, I just see the screen stop sharing now, but that's basically the end of the lesson.
So,
Yellow, talk to me.
I want to ask, in the textbook, with the halogenoalkanes reflux, they talk about using an alkali.
Correct. Now, I looked at that very carefully. I don't have your syllabus on my, hang on, I'll share it on the screen quickly. I'll share the syllabus from my computer screen. But you're absolutely correct. That's another possible one, but the textbook or the syllabus only wants you to know the hydrolysis. Just let me get it for you quickly, then I'll show you syllabus. There we go. And then I'm going to share that with you quickly. Share syllabus. Cool. And then just go.
I think they say it's just faster. It's the only difference.
It's possibly faster, correct. So you can keep that as an extra. You can add it to the notes. It's definitely something you can keep in the back of your mind. So you don't have to discard it. You can just add it to that. But I literally just followed the syllabus. So if you look over here, I'll highlight it for you. Are you seeing the syllabus? Sorry, on your side.
Yeah.
Good. Oh, sorry about that. Here we go. Nucleophilic substitution reactions, and it talks about hydrolysis, nitriles, and primary amines. And in this case here, I'm assuming the hydrolysis is implying the reflux with H2O. So I'm assuming that's this one. But you're absolutely correct. You can do it under alkali collisions as well, but then you wouldn't add the ethanol. Cool. So very good question. Thank you for that. I don't know if they took it out the syllabus. I would say keep it as an extra tool in your toolkit kind of thing. Yeah, but the biggest difference there is if you must not add the ethanol, because if you add the ethanol, you're going to get the elimination. So it's very important that when you do the substitution with the OH, you do it with just the OH, like sodium hydroxide, but you don't put it in an ethanolic solution. Cool, because if you put it in the ethanolic solution, you're going to get the elimination reaction. And the elimination is not what you want, because that's going to form the alkene. That's not going to do the substitution. Good. Any other questions? Otherwise, I'll let you go.
No.
Yep. Just have a read through the notes. It's quite straightforward. And then just very important, just always refer back to your functional group conversion chart, the map that I keep showing you, and just keep in your mind ticking off the different processes, and then daily or once every second day or as often as possible, just constantly revise those processes, because you're literally going to see them coming up everywhere. I mean, we're not going to escape them. Cool.
So,
okay, sir.
You guys be good. See you tomorrow.
See you tomorrow, sir.
Bye.